Hello friends, this is Arti Karnuke, Assistant Professor in Civil Engineering Department at Tulsiramji Gaikwad-Patil College of Engineering and Technology, Nagpur, accredited with NAC A+ grade. I welcome you all in the next lecture of Pavement Analysis and Design. So, in this lecture, we are going to discuss about the Burmister Theory and Triaxial Compression Theory. So let us discuss one by one. First, we will going to discuss about the Burmister Theory and after that Triaxial Theory. So let's start. So Burmister Theory is also known as the layer system theory. So Donald M. Burmister developed the layer system analysis in 1943. So, as known, the flexible pavement section are composed of layers and the elastic modulus of the top layer is the highest. So, the total mass of the pavement of a subgrade does not passes a constant E value as assumed by the Boussicault in his analysis. However, Boussicault's analysis can be considered a special case of the Burmister layer system analysis. So, the effect of the layers above the subgrade is to reduce the stress and the deflection of the subgrade. So this method of analyzing a two-layer soil system which resemble a flexible pavement having its top layer stiffer than its bottom layer. So later in 1945 he extended the method to included three-layer system as well. So as an important outcome of the Burmister numerical solution, the flexible pavement thickness design method was developed for a air-filled pavement. So if the layer of a soil subgrade, subbase cores and the base core are assigned elastic moduli of ES for subgrade, ESB for subbase and EB for base, then as per Boussicault analysis it is considered ES is equal to ESB is equal to EB, whereas in the layered analysis it is taken as EB is less than ESB is less than ES. So the vertical stresses on the modular ratio, it is the E1 by E2. Then the vertical stresses decreases considerably with the increase of the modular ratio. So the effectiveness of the reinforcing action of the pavement layer is logically utilized in the Burmister approach. So basically there are some assumptions in this approach. So it is an example of let us consider that so basically this is the graph variation of the subgrade stresses with the modular ratio. So here as you can see that the different modular ratio, that is E1 by E2 is given for the particular stresses. So as I told you that there are some assumption which is made in for this method. So let us discuss about the assumption. So the very first assumption is that the material in the pavement layer are isotropic, homogeneous and elastic. So the pavement forms a stiffer reinforcing layer having modulus of elasticity higher than that of the underlying subgrade in two-layer system. So then the second assumption, as we said that the upper layer, that is layer 1, is weightless and is of infinite extent in the horizontal direction, but of the finite thickness, the lower layer, that is subgrade, it is infinite in the extent both horizontally and vertically downward. So the surface layer is infinite in the horizontal direction and finite in the vertical direction. The underlying layer in two layer system is considered infinite in the both direction. So next is the if the layer are in the continuous contact, the top layer is that of shearing and normal stresses outside the loaded area. So basically here they are giving a boundary condition. So first is the surface of the upper layer is free of a normal and shearing stresses outside the limit of the loading area. Next is the at the infinite depth, the stresses and displacement in the subgrade are equal to 0. So every layer, as we already discussed in the previous slide, that the every layer material is the homogeneous, isotropic or ideally elastic. So they are characterized by a unique elastic modulus and Poisson's ratio. So as we discussed that the pavement consists of the two layers, the elastic modulus value of the top layer is more than the bottom layer. So that is E1 is greater than the E2. The solution of the two layer problem satisfied the continuity condition of the stresses and the displacement across the interface between the upper and lower layer. That is, at the interface, the normal and shearing stresses and the vertical and horizontal displacement are equal in the two layers. So basically the interface between these layers is rough and there is no loss of a transfer of the applied stresses from the top layer to the bottom layer. So there will be no shear and normal stresses outside the loaded area. So the applied stresses is uniform over a circular area. So after that, the comparison of the vertical stresses distinguish between the Bossington single layer system and Burmister two layer system. Assuming a pavement of a consist of a single layer having elastic modulus EP lying over the subgrade with the elastic modulus EP. So it is observed that the vertical stresses on this subgrade is reduced from 70 to 30%. By introducing a pavement layer of the thickness equal to the radius of the load, or H is equal to A. So elastic modulus 10 times higher than the elastic modulus of the subgrade soil. So that is, we can say that EP by ES is equal to 10. So the Burmister approach therefore they utilize the reinforcement action of the pavement layer. So the deflection factor F2 is introduced in the two layer system, which is depend on the ES by EP and H by A. So in another terms, ES by EP is nothing but the E1 by E2. So the deflection equation given by the Burmister method. So for the deflection under the flexible plate, it is given as del T is equal to 1.5 P into A divided by ES or E2 into F2. And deflection under the rigid plate, it is given as del T is equal to 1.18 PA divided by E2 or EP into F2. So by introducing the additional pavement layer over the subgrade, the vertical stresses induced on the subgrade exactly under the center of the loading plate can be reduced from the 68% to 30%. As we already discussed that it is the range from 70 to 30%. So to make this possible, the radius of the additional layer has to be equal to the radius of the loading plate. So the elastic modulus value of the additional layer has to be approximately equal or 10 times the elastic modulus value of the subgrade, as we already discussed in the further slide. So it is nothing but the E1 is equal to 10 times of E2, and the Poisson's ratio of the both the layers has to be equal to 0.5. So due to this reason, construction of a pavement is carried out in the multiple layer instead of the single thicker layer. So here E2 is the modulus of the lower layer, that is subgrade. F2 is called as the deflection factor, which is dimensionless, and it is the function of both ratio of modulus of elasticity of the subgrade to that of the pavement and the depth to the bearing radius ratio. So in the chart we shows that the value of the F of various depth ratio and moduli of the elasticity. So the deflection factor F2 is introduced in two layer system, which is depend on H by A and ES by EP, that is E1 by E2. So P is the tire pressure, so this is the graph, vertical surface deflection for two layer system. So this is the graph between two layer deflection factor, that is F, and the thickness of the reinforcing layer, that means multiple of radius of the contact in the with the tire. So this is the comparison of the vertical stressor distinguished by Burmister and Bosque approach. So as we already discussed that the vertical stress is induced on the subgrade and exactly under the center of the loading plate can be reduced from the 70 to 30%. To make this possible, the radius of the additional layer has to be equal to the radius of the loading plate. So by introducing a pavement layer of the thickness equal to the radius of the load, or H is equal to A, having an elastic modulus 10 times higher than the elastic modulus of the subgrade, that is E1 by E2 or EP by ES is equal to 10. So Burmister approach therefore utilize the reinforcing action of the pavement layer. So due to this reason, construction of the pavement is carried out in the multiple layers instead of the single thicker layer. So next method is the triaxial compression method. So these are the contents of the triaxial compression method: alternative test, apparatus, test procedure, advantages of the triaxial test, disadvantages of the triaxial test. So for calculating the shear strength of the soil, basically there are four methods which we can use for measuring the shear strength of the soil. Direct shear test, it is also called as the box shear test. Then triaxial compression test, also known as the triaxial method as well. Then unconfined compression test. Then the vane shear test. So in this lecture we are going to discuss about the triaxial compression test. So basically first we will focus on the which apparatus is used for the triaxial compression test. So basically it requires axial loading piston, then cell pressure gauge, then dial gauge measuring vertical displacement. I will show you in the figure as well. Then the specimen membrane, then pore pressure gauge, then pore fluid drainage valve, open and closed valve. So basically this is the diagram. As you can see, This is the vertical gauge measuring vertical displacement. Then this is the axial loading piston. Then this is the cell filled with the fluid. Then these are the soil specimen. This is our soil membrane. Then this is the cell pressure gauge denoted by sigma 3. And this is the pore fluid drainage valve, open or closed. Of course now it is open. And this is the pore pressure gauge. So the objective of the trial axial compression test is to determine the shear strength of the soil under the lateral confinement. An attempt is made to simulate the confining pressure observed in a loaded soil mass. So in the test setup, it is possible to provide uniform fluid confining pressure only. So the cylindrical specimen of height to diameter ratio 2 is inserted in the thin membrane. A saturated porous stone is placed on the pedestal and the cylindrical soil specimen is placed on it. So the specimen is encased in the rubber membrane and sealed to the pedestal at the bottom as well as to the loading cap at the top by rubbering a ring, and the membrane is used to prevent the water from penetrating into the soil sample. So the triaxial cell is filled with the water and pressure is applied to the water, which in turn is transmitted to the soil specimen all around at top. So this pressure is called as the cell pressure. Now the test procedure. With the cell pressure held is constant, additional axial stresses, that is PD, is applied through the ram gradually until the sample is filled. So these additional axial stresses is called as the deviator stress, which is denoted by the PD. So there is we will discuss it in case of the phases. So first is the drainage condition. So these are some parameters which we have to taken care while performing the test. So first is the cell pressure added, like P3 increases. So basically these are the representation of the diagrammatic, and it is required while we are going to actual designing it. So basically these are the some parameters which is required. So as you can see, consolidation phase 1, that water is filled in the cell, which create pressure, that is P3 of course, which create pressure on the specimen. Then the next is the shear drainage condition. So drainage, of course, here the symbolic representation is D. So you have to remember the symbolic representation as well. So in that case, drainage wall is open so that the no excess pore pressure. Then after that, the undrained, it is denoted by the U. So in that case, the drain wall is to be closed. So if we are close the wall, so of course there is no change in a volume, and the extra pore pressure will be generated on the specimen. So we gradually increase the pressure at the piston until the specimen fail. So the normal load is applied through the vertical piston by means of a strain control machine, and the maximum vertical load at the failure is recorded. So the specimen are usually subjected to a constant strain rate of 1.25 mm per minute. Usually the lateral pressure is maintained constant and the vertical pressure is increased until the specimen fails. Then these are the types of the triaxial test. So first is the unconsolidated undrained, denoted by UU. Then it is also called as Q. It is also denoted by Q, or it is known as the quick test. After that, the second type is consolidated drain, denoted by CD. Then after that, it is also called as it is also denoted by S, or a slow test also known as. After that, CU, consolidated undrained, it is also denoted by R test. So you have to remember the symbolic representation as well. Next is the so of course first is the unconsolidated undrained, that is UU. So basically this part is used while we are going to designing it. So next is the advantages of the triaxial test. So basically the shear test under the all three drainage condition can be performed with complete control. Then the pore pressure and volumetric changes can be measured directly. The stress distribution on the failure plane is uniform. Test is suitable for the accurate research work. The specimen is free to fail or the weakest plane. The state of the stress during any stage of the stage is known. So the Mohr circle can be drawn at this stage of the shear. Then the disadvantages of the triaxial test. So in case of the drain test, the test can be take longer period as compared with the that in the drain shear test. So this apparatus, of course, it's a bulky and very costly and elaborate. So this is all about in today's lecture. We will discuss more on it in the next lecture. So thank you.